And so my name is Scott Wiseman. I'm here to talk about Kafka, of course, and you know, you can read. And basically, from a company, SoFi, we have a strong presence in Montana, currently focused on a large development staff in Helena, Montana. We have over 100 people there. We'll talk a little bit more about that. To start with, I was kind of struck by the keynote speech in that there's a little bit of overlap in some of the themes here. This is kind of a presentation about growth and scaling. It may be a slightly different type of scaling than he was talking about, but how do you deal with those? And I'm coming at it more from the technical perspective. So for that reason, we'll talk a little bit about the company and how we're growing and our technology within the company and why we were thinking that Kafka may be an interesting solution for us. Exactly what types of problems it would solve, and followed by lessons learned, things I would do the same way again, things I would do differently, and you know, also kind of address things we found out, things we learned, we didn't expect going in, but turned out to be good things as well, if that makes sense. So to start with, just a little bit about the company and what we're faced with. That handsome devil up in the left corner there, that's Mike Cagney. He's our CEO. He's one of the founders with a couple of other guys back in 2011. We started student loan refinancing in May of 2012. We introduced other products. So we're, you know, over time, in a fairly short amount of time, expanding product lines, but also growing the business at the same time. April 2015, we had surpassed $2 billion in funded loans. By September of the same year, we were at $4 billion. So the growth kind of, the rate of our growth, you know, kind of escalating. Also acquiring other companies. Back in February of this year, we acquired another a startup company called ZenBanks. And so that's causing our architecture to change and things to change rapidly for us. At the same time, we had a lot of changes in our development staff. And so back in 2014, January 2014, we were at 9 software developers. 2015, it was 25. A year later, I believe that number represents 55. In 2016, December of the same year, we were at 100. Today we're at 180. We've added 80 developers in so far just this year. We're looking at adding, I don't know what the number is right now, Dave, maybe 80 more by the end of the year, somewhere around there. So in 12 months, we would have more than doubled our software development staff. And when I talk about scaling, scaling horizontally and having the technology scale is one thing, is one type of problem you need to address. And you know, all internet companies kind of start the same way, right? And they start with developing a monolithic application that you can deploy out. I mean, it might be a WAR file or EAR file, but you're deploying out a large, you know, application that has all of your core business logic contained within. You have the user interface, you know, you have a few services backing it, and you know, you have a persistence tier. The problem, well, let me put it this way. That's actually not a problem. That's actually the right thing to do early on in the company. There are distinct advantages to deploying a monolithic application. You have easier debugging. All your calls are, you know, in JVM, they're synchronous. It's easy for developers to trace through and figure out what's going on. Scaling may be as simple as dropping in another system, you know, that kind of mirrors that, and then just load balancing between the two, splitting your traffic, sticky sessions or something to that effect. It's not exactly how we started, but we had an awful lot of what looked like a monolith. There are a few supporting services around the edges, but the core business, really, we could have been running it on the one application. And with that comes some real problems. It's you know, you start to split out the separate services, and the concept from domain-driven design is basically to carve out domains and split them out as their own service that's independently deployable. And ideally, the persistence used by that service would be co-located with that service, and one team can really have knowledge about how to stand up that service, develop it over time, and publish an interface to the rest of the company. The problem is we relied very, very heavily on synchronous REST calls between these services. The thing about the synchronous REST call is you're still synchronous. It's still somewhat easy to reason about from the developer's perspective, but the problem is we still have a monolith. We just happen to have a distributed monolith that has all the failure modes of a distributed application. So when you have REST services communicating to each other and the REST services going in multiple directions and farmed out across all these different services, it's very, very difficult. It becomes much more difficult to trace through what has gone wrong. But unless you kind of buttress your REST calls and protect those with things like, sorry, I lost the word, but essentially what you want to do is have automatic retry built in, potentially exponential back off of retries, caching of data. There are a lot of strategies in order to support making synchronous REST calls between your services. We didn't do a good job on a lot of those, and so failure mode was something downstream would fail, not necessarily critical to the business, but exceptions would be thrown in another service and then cascade up through the infrastructure, right? I think that's a common scenario in a lot of companies. When it's a distributed application, it's a lot more difficult when things are going wrong at midnight for the tech ops folks to go in and kind of trace through who failed, what was the actual point of failure. We got exceptions thrown from multiple services deployed within our stack, but what's the true origin of the problem? There are other problems that you encounter. For example, deployment. You make changes to the REST service. All clients to that REST service better be alerted. Ideally, the API changes are backwards compatible. We found that that's much more easily said than done. In reality, that's very difficult to trace through. It's very difficult when you're adding, 10 software developers a month, whatever the case is, that everyone understands the infrastructure enough that you can make intelligent decisions about how to migrate your service interfaces and communicate that out and keep everyone in sync. And so what we're really talking about is scaling in terms of people. When you add people who need to work on, understand, and deploy new services and new features and entirely new products within a complex infrastructure, how do you bring them up to speed in such a way that they understand all of these issues, all of the implications of potential changes they would make, and then make good decisions and write appropriate code? It really starts to become unmanageable. And so we're at this point where we have this distributed monolith, and we're wondering, how do I truly decouple services? And my teams work on services that are really downstream from some of the core business. How do I truly get them decoupled from everyone else? There are a few ways to deal with that, but going asynchronous is a good solution. And let me go to the next slide. So let's talk about the fact, let's start here. This is where we're at, and I'm going to use a simple example, which is a couple of actual service calls that we were dealing with up until we implemented Kafka within our organization. Here, this is a simplification of the whole thing, but we have a borrower service up front, taking information from our users. We have a registration process within our company, and when customer information, registration information is saved, it's saved in the customer service. Borrower service, that's synchronous, gets back a customer ID, and process continues. The next step in this process is actually a REST call over to the email service, which is, essentially, please send the registration email, welcome email to this person. Well, email service gets a customer ID and a little bit of other information, but actually makes a synchronous REST call up to customer service in order to get customer, and gets the information that it needs, and then actually goes out and sends that email. Any point of failure in here could end up disrupting the borrower registration process, which is kind of problematic for us, because whether or not they got the email, we don't want them to know that we failed, right? It's another way to think about the problem. And we'll discuss exactly what Kafka gets us, but it's a messaging bus, and it allows us to handle the asynchronous communication. And basically, these little blue dots on here represent separate messages being put up onto Kafka. The borrower service in this case publishes a user-registered event. The data it puts up on Kafka is segmented by topic. The topic in this case would be the user-registered topic. The user-registered event is simply a key-value pair. The key can be anything of your choosing. The values that we use are basically a JSON body representing the data for that event. That is, Kafka is extremely fast in terms of the serialization, in terms of the communication, and it's extremely robust. We'll talk a little bit more about that. But that becomes a store in the middle here from which various services can read and react to that user-registered event. The actual publishing of the data from the registration service is extremely fast. It's extremely lightweight to write a producer that actually publishes that up to Kafka. So it's kind of a fire and forget of this. In this model, we have two things going on. That customer service we spoke about before is now an event consumer and consumes that data and stores it away for future use. At the same time, the email service can react directly to the user-registered event. There's no more synchronous REST calls. If I were to bring down the email service for maintenance, for upgrading or whatever, I'd bring it down, I'd bring it back up. That would not be known to the other services. It would not put our infrastructure at risk, in real time. And it would still be able to pick up where it left off in terms of processing the user-registered events and sending the emails with that data. Does that make sense? So, asynchronous model with Kafka in the middle, and let's talk a little bit more about the fact that, next slide. What's cool here is that none of the services need to know about the existence of any other service. We're going from a model where we're kind of have a central touch point orchestrating what should happen and making synchronous calls in order to make that happen, more to a model where we can stand up services that are choreographed and just react to facts, react to the data that is published onto Kafka. And for that reason, we can stand up a fraud detection service without ever alerting anyone else that even exists, right? I can just hook into Kafka to the data being published and have that fraud detection service. If fraud is never detected, no one ever has to know about it. Now that's important enough that if there is fraud detected, maybe then you make a REST call to one of the other services in order to interrupt what's going on or to be able to take action, right? I'm not saying that you completely replace REST within your organization. There are places for it. Things like security and authentication or business to business, right? That's a perfect place to you're going to expose a REST service. But our hope is to greatly minimize our reliance on synchronous REST calls within the organization. Here in this case, we have a user registered event. If they had opted in for text messages during the user registration process, that would be carried down as some of the data within that user registered event. The SMS service does not need its own REST call at that point. It can inspect that data, see that they opted into receiving text messages, and go ahead and send the text message. So it's very easy for us to compartmentalize, our code, but also the people working on these services, and allow them to do their work, stand up their services, and get their job done without having to understand the entire infrastructure of the organization. They don't have to communicate with these other teams about REST interfaces or migrating REST interfaces. They're just looking at the data as it's published and made available throughout the organization. Kafka is that central touch point for us where that data is published, for that sharing of data. Well, we're getting there. So, what is Kafka? It's an open source project. Some people at LinkedIn started in on it in order to build out LinkedIn. Wasn't that long ago, I think 2010, 2011 timeframe, they open sourced it. It is a publish-subscribe model, as I spoke about. It scales fantastically. So there are examples of companies running Kafka clusters with tens of thousands of topics. All of those topics with different events published. Various services within those organizations listen to multiple topics, or one or more topics, and then build services around that. All data shared. So examples of companies doing this: Netflix, heavily reliant on Kafka. LinkedIn, of course. Amazon, and let's see, another company, a telephony company, Interactive Intelligence. Companies that have to deliver a number of services and expect high availability and have a lot of software developers are starting to go in this direction. You see a lot of talk about it and a lot of momentum around it. Basically allows you to process streams of data. Now, it's probably a good point to bring up that there is some overlap in terms of why not use something like JMS? The argument for using Kafka is that the messaging is faster. I'm from Boston, so I like to say it's wicked fast. It's extremely lightweight. The message overhead is about 6 kilobytes, whereas a JMS message, because of the complexity in the protocol, is about 160 kilobytes. It runs, it's designed to run as a cluster and be extremely fault tolerant. So when you stand up a Kafka cluster, you're standing up an odd number of nodes. Right now we have 3, and it runs on top of Zookeeper, so you need 3 Zookeeper nodes. But you can drop any one of those nodes and the cluster will still be available. In this case, with the example of 3, you can drop 1. You stand up 5 nodes, you can lose 2, the cluster's still available. So you always need more than one half of the nodes up for the cluster to be available. Any data that you publish is shared out across multiple nodes and persisted at multiple nodes. So there are 3 APIs that come with Kafka. There's the producer API, I kind of alluded to earlier. There's the consumer API that allows you to very easily pull these messages down, process the data. There's also a streams API. And that's one of the big differences from JMS right there. You start to build within your tool set the ability to process streams and do some more advanced data analytics type stuff right within your projects, within the services that you stand up. We'll talk a little bit more about that later. As I said before, each record is really just a key value and a timestamp. It's very lightweight. The timestamps provided for you, that's just part of Kafka producer producing the message for you. These APIs are fairly simple to use, easy to configure. What else can I tell you? That's probably a pretty good start. Now, one thing that we're doing is we chose Apache Avro, another open source project for serializing the data up onto Kafka. The reason is that it's extremely fast data serialization. Avro supports schemas. All of our data that we publish to Kafka has an associated schema for that topic. And the schema, you get the obvious benefits of the schema, right? You're forcing developers to conform to the schema anytime they publish anything up. If they attempt to build a message that does not conform to the schema, it's rejected. So you're protecting your data that's published. The other thing is that we're requiring all documentation with every single element on every schema. So all of your data that you're publishing and making available across services within your organization, that's a central touch point to provide documentation and communicate to other teams about what that data truly means, right? Anyone who has any experience in software development knows that, just taking data within the organization, it changes meaning over time. What does this timestamp mean? Was it the point that they registered, or the point that we processed that registration, or something else, right? So we want to be very explicit about what shows up on Kafka, and that hopefully you can just read the schema for the data that's going on that topic and understand what you could do, what that could mean to you. It has bindings to many programming languages. In Java, for example, we actually have all of the schemas in one of our Bitbucket projects. And during the build process, we compile those down into Java objects that allow you to easily write your data for that particular schema. So publishing data on Kafka for us looks like populate all the values in a Java object and then call the Kafka producer that we've pre-configured in order to fire it up onto Kafka. So kind of cool. And like I said, it ensures data is high quality, documented, and usable at scale. One of the great things here is that the company founded by the creators of Kafka, they left LinkedIn and founded a company called Confluent. They've made some other software, open source software extensions for Kafka, and they created a schema registry that runs on top of Kafka. That schema registry is where all of our schemas get published. And so that is co-located with Kafka. That's freely available. And that's a great thing because the schema does not have to be within the payload itself. So any producer and consumer that's going to produce a message and put it up onto the bus actually communicates with the schema registry and pulls a schema down if it doesn't yet have it locally cached. These schemas are very lightweight, and so it's not going to create a problem with a memory footprint or something like that. But that's kind of provided for free. So there's a serializer specifically for using the schema registry and for Avro. It's freely available off the Confluent website. That'll assist you in pulling all of this together. So it's fairly straightforward to get a nice architecture there where your data is all being published according to a schema. You have the very fast serialization of using Avro. You have the language independence of the fact that you're using Avro, and with the bindings to various languages, they make it very simple to pull it all together.
What's the interplay of the schema registry and the static code that you generated from the schema in your?
Yeah, you know what, I in reality, when it compiles that's a good question. It compiles that Java object, it kind of shoves the schema in there. Mm-hmm. The schema register, because if you do it that way, you're shipping the Java object, you're pulling it in as a dependency, you kind of have the schema with that object, and the serializer uses it from there. In reality, other mechanisms, it would go over the wire to pull the schema. So really, I glossed over it. There are two ways that it can work.
Okay.
Yeah, but good question, good catch.
Scott, is it easy to migrate and upgrade schemas?
Oh, yeah, thank you. I skipped over one very important point. We enforce backwards and forwards compatibility. So we force the developers to think very carefully about how they're going to migrate and what data they're going to introduce. So with Avro, during that compilation, during the build process, we actually check, is this schema forward compatible, which would mean that any messages in flight could be read, could be converted into the latest version or backwards compatible. Can the latest version be read by a previous version of the schema? And you have to think about the implications of that, but because we enforce both, you have to be forwards and backwards compatible. You can add, for example, a new element to a schema, but you would have to ensure that there's a default value there for it, for example. There are certain things that you can't do easily. You can't add new values to an enum easily. The whole reason is that you might have messages in flight, maybe only for a few milliseconds, but as you bring up a new schema but you still have messages according to the old schema, you don't want your new consumer to be unable to process that. You don't want exceptions to happen. So if you are introducing breaking changes to a schema, we decided that we would take the overhead of having to introduce, because Kafka will scale up to tens of thousands of these topics, add a new topic. So breaking changes go to a new topic, and then you deprecate the old one, giving your consumers, 3 months, or you choose, but some amount of time that they can roll over and begin dealing with the other topic. That the previous topic will be archived. Does that make sense? Yeah, because we have tens of services that are going to be publishing to this in short order. We can't rely on the fact that everyone's going to be able to migrate their code at the same time at the same rate. Yeah.
Do you produce on both topics simultaneously for like 3 months then?
Yes.
Okay.
Yeah. Yeah. Yeah, so there's a little bit of overhead there. So you can think very carefully about how you want to structure your data, and how you want to do your data governance and where your service is going to go over time. Or you could not put a lot of thought into it, but you may incur that overhead later on because, we didn't think of that. But we've got a path either way, right?
When you talked about the patent checking, do you use the schema registry for that, or is there something external to the schema registry that provides that?
Oh, the compatibility checking happens during our build. That's a.
Is there some tool that you're using for that, or do you have saved files?
Yeah, the schema registry itself.
Okay.
So we actually, yeah.
Okay.
Yep.
That's to say, during your build, you're reaching out to the schema registry and asking it, is this okay, or?
I'd have to double check.
Okay, sorry.
Either I think he just pulls in one of the libraries from the schema registry.
Neat.
Yeah. I'd have to double check for you, but. And the fellow who wrote it's in the building, so. See me later. So the big picture, I'm not saying we're here yet, okay? Ideally, that hairball that I showed you earlier would be a little bit easier to manage. Some of this is reality, right? I've got email hanging off of Kafka now. I've got some of these services, and SoFi people, I changed names for clarity. Leave me alone. I have some of these services publishing events now, and so we're starting to make progress and moving in this direction. We still have a large database schema sitting in the middle. That's a single touch point that's preventing us from truly deploying these services as microservices, as independently deployable units. However, we're starting to split out the schemas and go in that direction. So customers does in fact look like this. With another customer's release, all data, customer data is going to be ending up on various topics up here. And because this is a true microservice, we've got control over that. One small team can manage all of that functionality, just publish out what it knows about customers. Everyone else just listens in on Kafka, on that central bus. My schema registry's hanging up here. in an ideal world, it would look like this. You're still going to rely on some synchronous REST calls. You're still going to expose REST to the outside world, that kind of thing. But ideally, your infrastructure becomes more manageable, and ideally, I can start to get this team to focus in, and they don't have to have a whole lot of understanding about, what my email team is doing. Our only communication right now, my team handles this, for example, and others, but my only communication now is the schema for what we're going to publish up here. That's my only touch point with other teams. I don't worry about anything else. It's simplified my life. It's made me happier. I get more sleep at night. So that's been good stuff. But doesn't even end there. So there have been challenges here. Some of the challenges around, and I kind of lumped it under data governance, but who decides what is appropriate data to end up on Kafka? Who decides what the schema will be? In the case where I just showed you that slide and I pointed out customers, it's its own service, and it's a true microservice, and that's independently deployable, and it's got its own persistence tier, and no one else, ideally no one else would be directly touching that persistence layer. That's great. That's separated out. I can work with that small team, and they can publish, and we can agree on those schemas, and what that schema should look like is fairly straightforward for us. He knows what data he has, he knows how granular it is, and we decide, do we want to publish the whole object graph or just multiple topics across the object graph, right? That's manageable. We've got other concepts within the company, like just the concept of a loan is actually an extremely complex object graph. The problem is I don't have one microservice that encapsulates it. So the conversation about who publishes what about a loan and who's in charge of what data is really unclear at this point in some ways. In the monolithic application, you didn't have to worry about it. But if you kind of want to think about it in these terms, it raises some real questions and some real problems for us, because different people have different perspectives. Each individual service that kind of make up the loan process has its view, its data, but only that data it was concerned with at that point in time. So there's nothing that can publish an entire JSON document representing a loan to Kafka at any one point in time. So the data is fragmented out across all these different services, and I don't necessarily want it to look that way when it hits the Kafka bus. I want something that looks a little bit more unified and well thought out. And I don't want to bring the underlying chaos, and expose it up into that tier, right? So really it comes down to kind of using Kafka and going to microservices and thinking about your architecture in this way kind of go hand in hand. It's when you do that domain-driven design and you carve off that bounded context and you determine this should be handled by one service and have its own persistence, and it should be this API, and you have those discussions and you do that work, it's then that I want to have that discussion about let's publish that data and make it available up in Kafka. Up until that point, we've kind of been doing it piecemeal. I need to know about loan status, or I need to know about this particular event. We're gonna fire that up onto Kafka, but I have no topic that looks like the loan topic, right? Which is the point that I'd like to get to. Is that making sense?
Yep.
So challenges. Well, I just lumped it under deployment. Once you get over the initial pain, you're good. But initially, you have to stand up 3 Zookeeper nodes, 3 Kafka nodes. You've got your schema registry. Who's in charge of these things? Where does it get deployed? You have security concerns. Like I said, each node needs its own data, is backed by its own data file system. It needs somewhere to write its data. What should that look like? We have to have all data encrypted at rest. You just have things to think about. We deploy everything to AWS. AWS is much easier with stateless apps. This is very stateful. these nodes need to always be at the same host and port and have to be known to each other over time. We have to set it up a little bit differently than we deal with any other service within the infrastructure. There's a learning curve there, a few hurdles to get over. There's some excellent articles online at the Confluent website that we use to guide us to deploying this on AWS. Monitoring, Yahoo has a open source project. I think it's just called Kafka Monitor. We're about to have that. We have other monitoring. Kafka exposes JMX endpoints, which things like Datadog or some other cool monitoring tools will just attach to and start feeding you back information. But we needed to make Datadog aware of all of the nodes, the Zookeeper nodes, the Kafka nodes, and the Docker containers as well that they were contained within. So you have to understand what you're looking for and at what level you're trying to look at throughput and performance, but all that information's there. Security is interesting because they didn't have any security up until like version 9. So it's fairly recent, but now nodes can be pretty well secured. They support TLS for connecting to the nodes. Zookeeper does not until the next release, but pretty soon everything could be talking, or it could be TLS between the nodes, between the clients and the nodes, between the nodes and the Zookeeper nodes, and I see us eventually, being there. You can restrict or provide, authorization to who can access certain topics as well. So you can lock down topics, essentially strip out personally identifying information, and then publish it to another topic that you could open up, to anyone. All right, so when I first started, and I think I have a few minutes, when I first started thinking about this presentation, I honestly thought that would be the last slide. It turns out that we kind of underestimated what we had in our hands here. and just to illustrate, I had read about but didn't truly grasp what it meant to have a Streams API available to us. It's a simple client library. Now, lots of people do all kinds of stream processing by standing up a Spark cluster or Flink, and there are others. But you're talking about standing up new servers within your organization, having people who understand how to use those technologies, and what do you do with the data? That somehow has to be fed back into your organization and used and processed in real ways, right? So that's not a trivial thing to get to. What the Streams API does is it provides a very small library that leverages features provided by Kafka itself to allow you to work with these streams and query these streams of data within your application. And the library itself is 9,000 lines of code at this point. It's extremely lightweight, it has no external dependencies, and it communicates to Kafka on your behalf and allows you to realize these streams and essentially view them as in-memory tables and go over and sort, manipulate data, publish back to the streams. And from the Java 8 perspective, where you have streams processing available in Java 8, it looks really cool. Why would you want to do that? Well, I have to stand up a new service. We contracted with a telephony provider. We have many hundreds of people who are on the phones providing customer service on a daily basis. We're going to a whole new system. I have to integrate with this other company. Well, internally, I thought, well, they'll be firing messages down on Kafka, requests to make a phone call, someone in the loan process, collections, whatever the reason is. I'll be collecting those in my service and storing it off into a local table. I planned on standing up a relational database in order to store that information, cache that information. A REST API communicates out to this telephony provider. We push the phone calls that need to be made out to them. Call status and dispensation gets reported back to us through the same REST API. I have all of that managed within a relational database. I put hibernate over the relational database. I need a couple guys to do that. I have to do the testing about the ORM mappings. I have to think about the relational data. And then later on, once I have everything sorted out, I have to publish it back on Kafka and report back to those services, ultimately the status of that call or the result of the call. Seemed relatively straightforward. I didn't see this coming. Forget the relational database. I've got a stream over here that tells me that are essentially the call requests. I've got another stream for call dispensation. The same key links these two things together. The same key also links the call status. Through the Streams API, I can provide all of this without the backing of the relational database. All the data about the call should be exposed and made available to the rest of the company at will. This becomes my persistent store for my call requests. My call dispensations are just being published again. If I need to know for a particular call request what the dispensation may be, the Streams API lets me realize that in code and basically do a it's not a query, but a join between the two streams, and actually see for any given call request the dispensations and status. Furthermore, Kafka will store this as a compacted log. So if I had multiple call, I will have multiple call statuses coming in for each call request. The compacted log, it's only storing the last key message for a particular key per topic. Does that make sense? I'm not storing call status history. Call status actually goes through a sequence of call statuses, and I don't need the history. Kafka will store a compacted log version of that. Also, call dispensation will only be one, so I technically don't need a compacted log. But I'm saving on storage, and I'm only storing what I need in that case. If you think about it, a database table is a lot like a compacted log. Every single change to that database table over time represents a different message that ended up as one row within that table. So your database table is in essence a compacted log. I don't really lose anything by having a compacted log, around the status, because I would.
How do you define the retention time on one of the messages that hits the message bus?
Yeah, you can define it by time, by size. It's highly configurable. By default, it'll keep it for a week. Most of our topics will be the default. We have some topics that will keep it forever, but we just don't expect enough volume for it to make a difference.
Is that done by the producer?
No, actually, that's done by configuring the Kafka node itself. Yeah. Yep. I should say one of the features of Kafka is it achieves. Boy, I have so much to talk about. I'm sorry, I'm down to about 2 minutes, but you reminded me of something else. Topics are partitioned. That's the basic abstraction that gets you concurrent processing. If you have 16 partitions on a topic, you can stand up 16 consumers, and it will guarantee message delivery order per partition. As a consumer, you can actually select which partition it goes to, or you can partition, it will automatically partition by key. If it sees the same key, that key always goes to the same partition, therefore it's always the same consumer. Your guaranteed message order in that case, you're guaranteed message order for key, but not overall. Overall, one of your consumers could be working faster than others, and therefore messages that hit the bus after the fact were processed first. However, if you think about it, if you just design your system appropriately, and your key was, for example, your customer ID, all messages about the same customer would be processed in the same order. And that's usually the granularity that makes sense when you're thinking about concurrency. If overall you need to guarantee every single message processed in order, regardless of key, you're down to one consumer. That's you're single threaded. it's an important distinction, I guess. I just wanted to throw out, code examples are tough. I'm not going to walk you through it. This is actually, I just cut and pasted it right out of that 40 lines of code that represents that new service, okay? So where I thought I needed an object relational mapping tier and all of this functionality, I've got 40 lines of code, and I was like, oh man, how am I going to justify my salary in the future? Like, it's a little too fast, a little too easy. But this looks like Java 8. It streams. I'm doing a join on a couple of streams here. And we're doing some comparison, and we determine do we want left or right. We'll take the right value and fire that down, or something to that effect. Sorry, good.
How do you keep track of what the last value was that you processed? So when you fire this up, you get notifications for new things.
Yep.
How do you know if you missed things
Yeah.
while you were down?
Yeah. Now, you can have Kafka track, that's the offset, right? Each message has an incremented ID. You can track the offset yourself and make the message offset tracking part of your transaction, in which case you could enforce only once processing, but you have to take some responsibility. If you let Kafka track the offset, you have the opportunity for the consumer to crash and not report back that it processed those messages. Therefore, Kafka never got a new offset and will basically risk reprocessing messages. We deal with that. We would prefer throughput in most cases. So we'll take, I just make the service that's dealing with it idempotent, right?
Yeah.
I don't worry about processing a message twice. It happens rarely, but if I did, it has no negative consequences. Where there are consequences, you have to take some responsibility for tracking offsets yourself. Does that make sense?
Yeah.
It's actually a little bit more complicated than that, but there are good resources. I'll tell you all about it. I'm sorry, I've gone over.